And yes, so just so you know, what I said is fill out that thing on Moodle. You have until like next Friday. If you don't do it, you'll lose participation marks or points, or you won't get those participation points. And if you don't do it, I'm going to assume that means that you want to do it though. So if you don't fill it out, you're doing a lecture. Okay? Deal? Oh, you have no say in the matter. So. All right, is the mic, okay, everything's working, cool. So this kind of goes to what I think Matt was asking the other time about, like, well, you know, how do we decide who gets like selected or replaced and whatnot? And it comes, like, really all that matters is that you have a mechanism to do that. Two very popular ones, something called steady state evolutionary algorithms. That's where the population is kind of like, you've got like one array, you select two parents, you make changes, you get the new ones, and then you add them to that population. But there's a finite space, right? So we need to decide who leaves. Is it the parents? Is it the worst? Is it random? It's up to you. That's the steady state one. The not steady state one, the more discrete one, is where what you do, this is the one I almost always do, because I just find it a little easier, and it works well, is I have my population of 100. Great, I evaluate how good they all are. So I now know all of their fitness values. If I want to do selection, I'll just randomly pick somehow two parents. Maybe they breed, you know, they do crossover. I'm going to make a brand new population of size 100 and put those two in there. There's 98 spots left. Just keep doing this until it's full. Maybe sometimes I pick some and they don't have crossover. Okay, fine. No mutation, whatever. Just do it till it's full. That's the next generation. Evaluate them all, select new generation, and you just keep going. So it's more discrete, where the other one, the steady state, is more like a continuous process. The discrete one, I don't know, I like it, but it doesn't matter at the end of the day. Whatever implementation, however you want to build this mechanism, great. If you are working on an assignment and you don't even want to go with one of the popular ones, if you're like, you know what, no, I've got an idea, brand new idea, no one's done it, let me try this. Fantastic. That's awesome. That's in the spirit of like good evolutionary computation, because honestly, all the rules are fairly breakable. It's very, like, even the description is like, we need a place to replace, or we need a way to replace. How? Whatever you want. Yeah.
I'm having a bit of trouble trying to visualize how it's like with algorithms. So like, if the point of this is like to try and find the strongest one, is it kind of like almost like a smash of derby where they're all kind of against each other, or is it like one at a time, seeing who replaces the guy?
So that's how we do selection, and once again, however you want to do it. There's two popular ones. There's round robin, and then there's like tournament. Tournament's the easiest. Usually what people will do for tournament is just randomly select 5 and take the best one of the 5 as a parent and then do it again. You have two parents. Round robin is kind of like this idea, no, not round robin, roulette wheel. It's like, you imagine if you have a population size 100, imagine you build a roulette wheel with 100 wedges on it, but the size of the wedge is proportional to the fitness. So those that are better have a bigger piece of the roulette wheel, and those that have worse fitness have a smaller, and then you spin. We like these processes to have a chance of including maybe less good ones, because it's a good way to also keep some level of diversity in the population, which is very important. Okay, initialization, how do you start? Random a lot of times. You can seed it with already good solutions, but there are potential drawbacks with that. So if you're doing TSP, generate a bunch of random permutations and start from there. If you have a reasonably good permutation to start, maybe you throw a couple of those in the population, but the problem with that is it might cause things to converge too quickly onto that solution, and maybe that solution is a local optimum. So that could kind of backfire, but Anyways. Termination, when do you end? Whenever you want. Maybe you set a threshold. If I ever get a fitness value that's better than this, stop. Maybe I say run for 1,000,000 generations, then stop. Maybe you care about diversity in the population, and once it hits a level of diversity, you stop. Whatever you want, it doesn't matter. Fitness has improved after some number of generations, stop. All of these are workable. Usually what I do is just say run for like 1,000,000,000 generations, then I look at the results. And hopefully I get something good. So, back to talking about 8 queens. So place 8 queens on an 8x8 chessboard in such a way that they cannot check each other. And I don't think check is the right word, but they can't attack each other. This, of course, can be generalized to n queens, or you have an n by n board and you want to place them. But let's talk about 8 queens. And if you don't, raise your hand if you have played chess before. Okay, cool. So everyone has a sense of how the rules work. So how do we want to represent this? How do we want to evaluate how good a candidate solution is? How do we want to actually include that, variation? That's the genetic operator, the crossover mutation. How are we going to do that? How are we going to decide to do selection exactly? Because at this point, I've told you we need those things, but we haven't talked about specifics. Some of these are going to be very problem dependent. I mean, they all are really, but some you've got a little bit more freedom. Like fitness, representation, well, the representation has to work for the problem. The fitness needs to make sense for the problem. Genetic operator selection, well, yeah, they have to make sense for the problem, but maybe you've got a little bit more flexibility there. I don't know. So, phenotype. The thing I'm trying to represent is this chessboard. So how do we want to encode it? And I know we've talked about this. We're going to encode it with a genotype somehow. A 2D array encoding. It's a very direct representation, but again, remember, direct is kind of like direct and indirect are like relative terms. And one of the key things we care about our representation is that it can fully represent all possible correct solutions. This encoding absolutely will. If it's a 2D array where you have 8 things in there that represent the 8 queens, it will absolutely represent all possible configurations. And you could do this. You could build your GA to work like that, and it will work. But you might find a little bit of a better representation. You might find that a different representation might work differently. Might give you better results, maybe worse, I don't know. But this one here, I'm willing to bet will give you some pretty darn good results. The idea is, it's just a permutation. What we have here is, if it's an 8x8 board, I'll have an array of size 8. Each cell contains a number, and the number in that cell represents which row the queen is in that column. And I guess here we're using 1 base counting. So the first column is in row 1, row 3, 5, 2, 6, 4, 7, 8. That's the idea. Can you yourself go from, if this is the encoding, if this is the genotype, based on what I just described, you should feel comfortable going from the genotype to the phenotype, what it means. Where we see the benefit here is we have drastically shrunk the search space. We have eliminated the possibility of putting all 8 queens in row 1. If we guarantee that this is length 8, we only have 1 index in that array for each column in the chessboard, and we guarantee that this is a permutation of unique numbers, I can guarantee that I won't have 1 and 1, which would mean they're in the same row. This encoding is clever because it shrinks the search space down to only solutions where we can't put more than 1 queen in any column, because each column only has 1 value that represents which row it's in. So we could only ever have one queen in each column, and if we guarantee that each number here representing the row is unique, we could only ever have combinations that have queens and unique rows as well. Which is good, because we know that if we had a 1 and a 1, we're guaranteed that that's not going to be a correct solution, because we have two queens in the same row, that means they can attack each other. Similarly with columns. We still have to deal with the diagonals here, but we've kind of eliminated the problem of queens in the same row and columns with this encoding, which is really clever. I want to be very clear. When you go out on an assignment or on your final project and you're working on something, coming up with a good representation is very hard. Very, 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 very hard. If you're thinking like, oh, well, you know, I showed you the 2D one, and yeah, I guess maybe this is kind of obvious, and this is way better. Making that jump is going to be very hard. And I'm not expecting you to come up with like, oh, that's a really good encoding. Wow, mind-blowing. If you do, fantastic. But coming up with a good encoding for a problem is a difficult problem in and of itself. So just be warned about that. I'm just showing you these differences can have huge consequences for the evolutionary algorithm. Permutation 1 through 8, yeah. This is more indirect than the other, that's for sure. And it does not contain all possible board configurations. But it does have all valid configurations for 8 queens. Any questions about that? Because the quietness, it's very quiet. And I don't know if that's because you're all like, yeah, I get it, come on, move on. Or because everyone's just kind of like, so I'll just keep going at this pace then. All right, so population. Our population is a collection of these permutations. Yes?
So in the representation, the number should be unique in every example, like in another example, not in the 8 queens, like in other example.
Yeah, you could, like think of that bit string, right? The numbers, my encoding was an array of 0s and 1s. I could have all 1s, all 0s. But in some problems, like TSP or N queens, going from something like have any digit between 0 and 100 in each array location representing the permutation to having only unique numbers shrinks that search space. So we don't need to do that. Sometimes coming up with a clever representation, like, well, if we make it a permutation and we decode it from the genotype to the phenotype this way, we might get some better performance or something. But it's the permutation, it just so happens that 2 of the examples we've seen so far have a permutation strategy, but we don't need to. Population, we've got a population of these permutations. The number in the population is a parameterable set, so maybe this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. I'm going to make a population of size 10, which is very small for an evolutionary algorithm. But it's population size 10. Pretend there's a unique permutation. Maybe they're not unique, but they're permutations. You know, I've got 10 of them. So I have now 10 possible candidate solutions. Fitness, count the number of conflicting queens on the board. Okay, we could do that, right? I mean, I'm not going to talk about what that algorithm would look like, but I'm confident at this level you could do that. Mutation, so, and I think Ethan, wherever you are, you mentioned this last time. If I want to do mutation, like the simplest type of mutation one could do is find one of the indices in your array, like think of that 8-length array, and just change the value in it to something different. There, we've added variation. But that's bad for a permutation strategy where the numbers are unique. Because if you make one change, like if I say, okay, we're going to remove 2, and someone yelled out a random number between 1 and 8. 3. Great, so now it's 3. Uh-oh, we have 2 queens in row 3. So that style of mutation is bad. But we can do this swap one. This is like this is like the simplest one for your unique permutation ones. Just pick 2 indices and flip them. You're not adding an extra number or you're just moving the place in which they are, which is fine. So this is a really good mutation because it's simple. I like simple things. And an idea that we'll talk about more later on in the course is about the level of like destructiveness the genetic operators could have. This is like minimally destructive in the context of this problem and this encoding and, you know. But if I said swap 6, that's going to be a lot more like shuffling going on. That's going to be a lot more destructive to the original genotype. You know, part of the point of the evolutionary algorithm is if I'm good, I want to pass on what's good to the next generation. But if I'm good, I make crazy amounts of changes and then I'm passed on to the next generation. Okay, that's fine. But now we're kind of moving towards a random search as opposed to a search that's kind of like progressed based on what came before it, right? So instead of kind of like moving nicely through the search space, we're gonna be like bouncing all over the place because we're making all these changes and it's crazy. Think of that example where I drew the bit string and the distances in a graph, right? If I do a single bit flip, the amount I'm going to move in this genotype space is going to be 1. I'm going to move to 1 vertex away. But if I make 3, I might move 3 away. So I've made a pretty big jump in the search space. Depending on the problem I'm working on, that might be good, it might be bad. Crossover, this one's tricky. I don't even know why I'm using this as an example here because this is one of the more complex versions of crossover. Probably my favorite simple crossover is 1-point crossover. Pick a point, and we saw that example with the elephants. Pick a point, index 4, there. The first 4 indices are fine, but everything after that gets copied from the other one and vice versa. So swap after some point, great. There's a bunch of other strategies we could do. You can make up your own if you want, it's fine. And we'll look at a bunch. But the problem with that strategy is if we did that, like here, imagine I did this and ignore this side for a second. If I was doing 1-point crossover, I would have, after the crossover, I'd have 1, 3, 5, 5, 4, 3, 2, 1, and 8, 7, 6, 2, 6, 4, 7, 8. Well, we got a problem. I now have duplicate numbers. So this right here, what is this one called again? Partially mapped or something? I can't remember. This one has a special name that I can't think of right now. But this strategy is just, it's based on that idea, but there's a bit of a catch. What you do is, all right, I want to cross over, so I've got 1, 3, 5, and then I want to add a 5, but I can't because 5 is already in there. So I'm going to go to the next thing, 4, okay, move the 4 there. Then 3. 3 is already in there, so I skip it. 2, all right, add the 2. 1, well that's already in there, so I skip it. Add the 8, add the 7, add the 6. So that's how I got it. Don't worry about memorizing this or anything. We'll talk about this more later in the course. And even then, don't memorize it, just know it exists. There are ways to do crossover nicely where you need to preserve uniqueness. And if you go to Google, you'll find a Wikipedia page on these crossovers. Selection, so there are so many strategies on how we do this. Randomly pick 5 chromosomes and take the best 2. Will that work? Yeah. Is it good? Probably. Maybe, in this case, if I want to replace them, select the worst 2 in the population with the new 2. Great. Maybe that's my strategy, but that's just one of an infinite number of ideas. And I would encourage you when working on the assignments and projects to get creative. Don't use the standard ones. Even if what you come up with ends up being crap, who cares? It's fun to try something new. All right, so maybe I'm going to set all these values now. Because genetic algorithms have a bunch of hyperparameters, a bunch of parameters we got to set. All right? So I need a representation. Well, it's going to be a permutation representation, right? N queens, you know, I'm going to do that. I'm going to do, oh, I guess the crossover is called cut and cross fill. I guess that's what it's called. Recombination probability, that's crossover. Recombination, crossover, same thing. If any two people are selected, they are guaranteed to do crossover. Mutation is that swap mutation, and it's got an 80% mutation rate, meaning, you know, they go to the next generation maybe. Oh no, not again.
Consistency. Just make a habit of reminding you every time.
Yeah, it's because it's, oh no, come on, let me open this. This one crashes fast too. It gives you like a 4-second warning. Woo! I made it. Yeah, hold the applause. All right, 80%. So the 80% is, okay, you know, we've selected the two. Roll the dice to see if we're actually going to do mutation. All right, if we are, okay, go do it, do the swap. Otherwise, just leave it alone. Selection, best 2 out of random 5. Survival selection, replace the worst. Find population size is 100. Number of offspring, 2. I don't really even know what that means. Random initialization, termination condition, solution or after 10,000 evaluations. Just an example of arbitrary values. Yeah?
Is the offspring like the number of children per parent?
I'm guessing, but to me it's kind of peculiar to note that because by default you would think that.
Yeah. Okay.
But I don't know. If I saw a 3 there, I'd be like, well, that's interesting. What are they doing? I see the 2 and go like, yeah, no shit. I don't know. I would also note that in a typical world, if you're doing like a genetic algorithm, or a crossover chance of 100%, don't do that. Crossover, you might want like, a good starting number would be like 80%. Mutation, you definitely don't want it to be 80%. That's going to be very destructive. Maybe closer to 20. And if you're doing something like genetic programming, it's probably going to be closer to like 5%. But just anyways. We'll talk about what are reasonable parameters as we go. So typical EA behavior. Imagine I have this one-dimensional problem, and the height there, I can move along the x-axis, and the height, the y-axis, is like how good that candidate solution is. And each point represents a candidate solution. So when we start here, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 candidate solutions in that 2D small search space. After a little bit of running, we'll see, some of the points, they start to kind of converge a little bit. They're moving towards good solutions. And then at the end, and it's funny, you can see this one here. It looks like it's going to get stuck in a local optimum, right? But look, if we go down here, we see it somehow escaped. Maybe we got lucky with a mutation. I don't know. But we'll see after time, it they'll converge typically. Another really cool thing, though, about this population-based strategy is, in this scenario, how many solutions do I have in the end? 2? I've got 9 there, right? Some are going to be very similar, but if I don't like this one, maybe I take that one. I don't know. But I actually get a suite of solutions that are all workable. They're all good. They're a little different. Some of them are more similar than others. That's fine. Yeah.
I was just gonna ask because you want to have all your solutions. I know one of the problems was finding the best solution. If you have already all of your solutions, should not just do some calculus to find the absolute maximum?
If you could correctly represent the search, the entirety of the space and the function that it's following, but usually we're using this stuff in spaces where we can't do that calculus. I mean, here, you could just, all right, tell me, give me the derivative, when it's flat, right? Well, yeah, because we know what the function looks like. But if we're studying, nonlinear relationships in fMRI data, yeah, good luck. It'd be great if we could. Here's a 3D version, whatever. Sometimes you'll hear things like exploration versus exploitation. This is not as well defined as some people seem to suggest. The main takeaway you should take from this exploration versus exploitation is there are certain aspects of the algorithm that you have that is going to be very exploring the space. We want to make sure our algorithm is capable of exploring the space pretty well. But there's also this idea of exploitation, where we want to take things that are good and exploit that to find other things that are good. And these things might be a little bit at odds, because exploring the space might be kind of like an emphasis on diversity of our candidate solutions, going out, spreading out across the search space. But exploitation is this pressure towards going up that hill, so to speak. So we got to be careful about balancing these things. You'll see premature convergence. You know, there's no, I think if you go with the, like, if you go back in time with some of the earlier representations, there are proofs of convergence. There aren't for more general problems. There's no proof, although it almost always does. In practice, I got to be careful, because if I say that, someone will show up and be like, well, I can make a problem that will break it, and yeah, you're right. Raise your hand if you've heard no free lunch before. Raise your hand if you've heard no free lunch in the context of AI, machine learning, heuristics. 1. All right, so the idea is, you know what, I'm pretty sure I get to it in a moment. So I'll just sit tight on that. Usually when you hit run, if this is like the plot, the best value in the population. So at every generation, I'm looking at what's the best fitness value. And here's the problem where I'm maximizing. Over time, we get better results. This curve, very typical. But like, it starts to converge, right? Like, it's like asymptotically approaching some value, it almost seems like. If this convergence happens, like here, look. Like, it's converged, I don't know, where would I select on here? Learning curve, yeah. Yeah, anytime algorithm, sometimes you'll hear this word, like you could stop at any point here and still have solutions. Just they might not be as good if you let it run longer. So here, like, this is the progress I made in the first half of the runtime, right? Look at that height and that fitness. We made leaps and bounds. But here we didn't make very much. And that's fine. In fact, for all I know, if I kept running, maybe it would shoot back up again. I don't know. You'll never know. But the idea of premature convergence is if you hit run, and this happens really quickly, where it gets really good really fast and then, you know, steadies out. Like, maybe your implementation was a little too exploitive. You didn't have enough diversity in your population to let it find other parts of the search space that also might be good. So premature convergence we don't like. What I would like to see is a learning curve that's maybe, you know, not as rapid and lets run longer, and I find even better results. You'll see countless examples of this, even when you start playing around with the code yourself. Yeah, when do you stop? Don't know. So this is the idea. If I'm solving a problem, and like TSP, and maybe I'm solving certain types of instances of TSP that have certain properties. So I'm not even looking at all the TSP problems. I'm looking at like a narrow subset of them. Maybe I can come up with a really clever heuristic, some algorithm that you know, guarantees some level of goodness or something, right? If you're focusing on that very specialized thing, you know, you might start getting really good results. You know what I am not doing? I'm not focusing on a very narrow subset of TSP problems, and that's like whatever. But you know what I do know? I know evolutionary computation. I know it gives me some pretty damn good solutions to problems. So your solution for the TSP one is really good on that narrow thing, which is fine. If you are looking for a better result, do that. But you know what? Evolutionary algorithms are just pretty damn good in general. You're probably not going to get the best result for TSP versus the person who's hacked together some amazing algorithm for it. But you'll get a good result, and you'll also get a good result for n queens with an evolutionary algorithm too. Also, random search, you know, it's fine too. Random search could work just fine. But it's that, like, it's the mechanics of the evolutionary algorithm that kind of takes the random search to a point of being very useful. And then, of course, do I say? Okay. Then there's no free lunch. Someone's phone's ringing. Turn it off. The no free lunch is this idea that there's no silver bullet algorithm. No algorithm is any better than any other algorithm at solving problems in general. And there's like a simple proof for it, is you can always design a crazy number of examples of specific problems that are designed to be very, damn, every year I forget the word. Adversarial problems, where they're designed such that if I know how your algorithm works, and you're making claims about it's the best algorithm, I can design an instance of TSP that is guaranteed to like give you the worst possible solution if you use your algorithm, right? So the idea is there's no one algorithm, there's no silver bullet. That said, in practice, we're going to get better results with an evolutionary algorithm over a random search. So be aware of no free lunch and its implications, but also be aware that, well, in practice, that theory is great, but in practice, with the problems that we're solving, maybe evolutionary computation will give us better results than just a random search. Ideally, we want an algorithm that will find the best solution. Fortunately, one exists, brute force exhaustive search. That's probably impractical for the problems that we're interested in here. And it's widely accepted that many problems just don't have tractable like algorithms for them. Sure, the brute force search will work, it's just, I don't have like 30 trillion years. And I'm not being silly when I say that. I mean, once those numbers get that big, 100 factorial, we're going to be needing to run all our computers together simultaneously for 30 trillion years. If you can do like a calculation of 1 million a second, like it's going to take forever. Actually, 1 million a second will probably be quicker than a couple trillion years. But point being, it'll take a long time. Many algorithms and heuristics exist for trying to find global optimum. They all have pros and cons. Local searches are popular too, but often lead to local optimum, which might be fine. If the problem here is like, if you're looking for a practical solution to your problem, imagine someone hires me and they have a delivery truck company and they want me to effectively do TSP to minimize their travel time, right? And they're like, okay, I need a good answer to this problem by the end of the day. I do. I'm going to pay you big bucks to do it, right? They need a good answer. They need a good solution. But if I'm just geeking out so hardcore about like, no, but I can get better, and no, I need to find the optimal, I'm going to do all this. Cool. At the end of the day, he doesn't give a shit if I squeak out epsilon better performance in a couple of days versus getting a pretty damn good solution by the end of the day. The other reason I'm saying that is sometimes as computer scientists, and I'm not telling you as this is advice for you not to worry about the implications and whatnot. I'm telling you because this is the struggle I always have, is where I start to geek out so hard about the algorithms and the math and this and that, when really, dude just needs his delivery schedule, right? So just, remember this sometimes. Hill climbing, yeah. EAs are great because they are population-based. That helps them escape local optimum. If I've got a bunch of solutions, hopefully they don't all kind of like land in the same local optimum, right? Works well with large discontinuous search spaces, and you get a suite of solutions at the end, right? Like if I've got a population of 100, they're all probably going to be pretty good at the end. So that's awesome. It's good with noisy data. Real-world data is terribly noisy, and it's pretty good working with noisy data. And yeah, that's an EA. Again, that was still fairly high level, but a little bit more precise, or more specific than the past one. So now we can move on to genetic algorithms. Our first big, special, specific idea. Genetic algorithms are, I would argue, based on what I know, far and away the most popular kind of evolutionary algorithm. They're good, they're easy. What more could you ask for? Again, it's still more of a framework than specific instructions, but this is going to be much more specific than we've been before. So a GA. So GAs are, most popular form of not even evolutionary algorithms, but evolutionary computation. But that's not to say they're a silver bullet, of course. Other strategies are great. Evolutionary programming, evolutionary strategies, genetic programming, particle swarm optimization. There's a long list of different types of evolutionary computation. When talking about evolutionary algorithms before, it was high level. Now we're going to start talking about specific implementations to solve specific problems. It's still high level though, like I was saying, is there's all these different things you can do to modify. That's one of the things I love about evolutionary algorithms is even as soon as you get to the specific thing, like, well, this is a GA, you can do whatever you want to try to see what your changes do to how good it is. So, what do we need? Well, we need a problem to solve. We need an encoding. We need a mechanism for initialization. We need a way to measure how good it is, the fitness function. We need a strategy for selection. We need mutation, crossover, and a way of like executing a generation. That would be like steady state versus discrete or something. Like, how am I going to do that? So for fun, this is what I was talking about yesterday. Did I lecture yesterday in this class? Yeah?
We would have, yeah.
I don't even know what day it is. I realize how cliche that is to say after like a year or whatever of COVID, but for real, like what is time? For fun, let's just evolve numbers to maximize. This is a very contrived problem. It's useless. Its utility here is to show you how it works. Don't use an evolutionary algorithm to find the largest binary number. Just write down a bunch of ones. That's better. But we can use it. So, encoding. Here's one, binary encoding. Like we were talking yesterday. We'll use array of zeros and ones. It's kind of like it's a little bit more of an indirect encoding. I mean, it's still like zeros and ones can mean like the number, but it's definitely further away from like a number than like the integer 17, right? It's still close though. It's relatively close. But you know, there's a bit of a gap there. We have to come up with a clever decoding strategy. The population will be an array of these arrays of zeros and ones. So here's initialization. Initialization population size. I need to tell, like, okay, how big do I want this population to be? All right, create a population array. For each spot in the population array, create a random array of zeros and ones. Add that new chromosome to the population. So create an array for the population, randomly create an array of zeros and ones, and then add that to the population. And do that until the population's full. There. Any questions about that one?
Yeah, so looking at the pseudocode, if you're writing the code for something like this, is it more common to just kind of use a library, kind of like how you would for machine learning, to use a library and then call specific functions, or would you be expected to write the entire thing?
In this course, for the GA, you'll write it yourself. For PSO, you'd write it yourself. For GP, you'll use, don't make your own GP system. That's a nightmare. I'm speaking from experience. It's painful. This, you would code it yourself. But here, let me show you real quick. Do I have it open? Yes, I do. Here is a GA implementation. A real quick and dirty one. All right? Here's my initialization. Oh, and this, I'm solving the problem of zeros and ones, that problem we're talking about. Here's my initialization. Initialization, I just made my population size like a global constant, okay? So for I in range population size, create an empty list. Then for I in the length of the chromosome, so how many zeros and ones do I have? Append to that list a random number a random int 0 or 1. And then once I'm done that for loop, append it to the population. And then I also have this thing, fitness. I'm creating a separate array to keep track of, like, index-wise what their fitness is. So index 1 of the population will have the fitness in index 1 match. FYI. But I mean, that's the same as the pseudocode. I'm just, you know, doing it in Python with some constant globals. Yeah, let's go back to the slide. You know, I'm just going to leave it in this view. If you hate it, I apologize. Because I might just bounce back between the two, and this will be a little easier. So fitness, you know, translate the binary encoding, the genotype, into an unsigned integer phenotype. Unsigned, we're not dealing with 2's complement. You all know what that means, right? 2's complement. Yeah. Fitness is the value of the integer. Goal is to maximize it, so this is super easy. That's 15, that's 17. But we saw this last time, that this can get kind of annoying because, well, getting to 16 requires a lot of changes from 15 in that encoding. We would have to change we have to change that 0 to a 1, and then all the 1s to 0s. That's a lot of changes. Just to get a little bit closer in the phenotype space. So an alternative is to count the number of 0s and 1s. Because now, it kind of gives us maybe a nicer gradient or pathway to a good solution in the genotype space. Because now if I'm counting the number of 0s and 1s, sure, the top one, like in this particular scenario, the top one has 4 and the bottom one has 2. But the top one is closer in phenotype space to getting to the max value, right? It only needs to make 1 change, where the bottom one needs to make 3. So there's that trade-off. So you may, though, think well, okay, so the second fitness idea is clearly superior, but if I had the number, does this one work? 0, 0, 1, 1, 1. Doesn't work very well. Can you see it at the back?
Does it depend on the problem that you're doing? Like, if you use either genotype or phenotype fitness?
Well,
or you have to, or do you kind of always use kind of a mix of both?
it'll depend.
Yeah.
And whatever makes sense. And you could get a master's degree by coming up with a very clever representation for a specific problem of interest. You know, even just coming up with it, hey, if we do this, and then decode it in fitness this way, that could be huge. It's not easy to do these things. It's not going to be obvious for a lot of things. I'm looking for my marker. All right, so if I have 0, 0, 1, 1, 1 versus 1, 1, 0, 0, 0. This one has 3 fitness with second strategy. This one has 2. So this one's better. But in the phenotype space, is it better? No. This is what? 4, 5, 6, 7. And this is 16, 8, 30, no, 8, 16, 24. Yeah. That's 24. So there's that trade-off. Another thing, too, is the gradient we can follow to get to a good solution. With this strategy, it's going to be very it's, the other one's discrete too, but this one is very chunky. We can have 0 1s, 1 1s, 2, 3, 4, or 5. Right? Imagine plotting that. Where if we do it where what it means as an integer, well, suddenly we can have values 0 to 31. What is 5? 2, 4, 8, 16, 30, yeah, 31. So 0 to 31. Still discrete chunks, but maybe there's a little bit that slope isn't like a steep or something, I don't know. They're trade-offs. So fitness, count zeros. For each gene in the chromosome, if the gene is a 1, count it. I could simplify this quite a bit, actually. Just add up the string of zeros and ones. 1 plus 0 plus 0 plus 1 plus 0 plus 0 plus 1 plus 1 will be the sum of all the ones, right? So, whatever. This is just perhaps a little bit more obvious. But there, that's the fitness. And then what it returns is the result. This is if I'm doing fitness 2. Then I want to calculate, like, if I'm calculating the fitness, well, that's the fitness for 1. I want to calculate the fitness for all the candidate solutions. All right, just call that function. Create an array of fitness values. This is how I store it usually if I'm lazy. You could make chromosomes be like an object that has like an array and a fitness value parameter or field attribute. You could. But I like to keep it bare bones, so I might just have like an array, and then another array that's just index-based. So here in population fitness, create an array of fitness values for each chromosome in the population, calculate the fitness of the chromosome with the function we just wrote, add that fitness to the fitness array. This should be, at this stage of your computer science, this should be like, yeah, no shit. Just call the function for each one, it'll do the trick. Selection. Randomly select a pool of some number of candidate solutions. Select the top one as a parent. Do it a total of 2 times to get 2 parents. There, you're done. And what's cool about this is it's good because it allows for potentially bad solutions being selected as a parent. If we always go and select the best, we're going to converge way too quickly. There's going to be no exploration. It's just we're going to lose diversity really quickly because the best ones will start to get closer and closer and closer to one another until they're all the same, right? So by including some of the ones that aren't as good, presumably if they're not as good, they're different than those ones. But, you know, if I hit run and I'm on generation X, where X is between 0 and 10 billion, right? If I've got some that are relatively good and some are relatively bad, and I select a relatively bad one, the reality is that relatively bad one, we're on generation X. It's still probably reasonably good. There might be something about that encoding that's useful. Maybe it's got like a vestigial organ that might come back into being useful. I don't know. So if I'm always selecting, if I do this with a pool size, if I have a pool size of 1 where I just randomly select 1, I have the possibility to pick the best solution or the worst solution. If I pick 2 for my pool size, I'll never actually be able to include the worst solution because I might pick the worst and then the second worst, but then I would compare them and only pick this one. So as the pool size gets bigger, we will be eliminating some portion of the worst ones from the population. They'll never have a chance to be evaluated. Point being, we might want that pool size, like we could tune it, but we might want to keep it relatively small. Selection. Population pool size. Randomly select chromosomes to fill the pool. Find the one with the highest fitness. Return it. Yeah. All right. We'll end bit flip. Mutation, just pick a bit, flip it. Crossover, 1-point crossover. Just do what I did before. We'll end here.